Okay. Yeah. Good morning, everybody, and thanks a lot to the organizer to give me the opportunity to be here today and share with you my thoughts about the origin of physical information. And I would like to do that because I believe that we are in a moment in, let's say, history where we could attempt to try to understand how nature computes the information universe. So from a bottom-up approach, trying to simulate and guess how this, which kind of information nature needs to compute our observation in the end. And instead of looking at experiments and trying to model what we see, we would like today to try to look from the eyes of nature. But to understand that, oh, they moved, sorry. And so information is a physical entity, says Ralph Landauer, but which physical entity encodes information? And if information is measured in bits, where are these bits stored, and how many bits are in one electron then? But before being able to answer this question, we need to understand what we are talking about. And for that, I really strongly agree with the point of view of John Bell that says information. Whose information? Information about what? Information is among the terms in quantum mechanics and in physics, but even outside physics, that is not so well defined. Sometimes we have many definitions of information, and I think, at least in physics, we should agree on a unique definition for information. So the final purpose is to try to be able to construct quantum states in a way that they comprehensively describe the underlying physical reality. So instead of using wave functions like we do in quantum mechanics that are only mathematical objects that tell us how about the probability of the measurements outcomes, we would like to see if we can build ontological wave functions that really encode the full system, the full information of the underlying system. So in that way, wave function like this one would not have meaning anymore, in the sense that they are too much generic. We don't know the details of the system we are describing here. And actually, we don't know how much information is in this wave function. Somebody could say, okay, it's a qubit, could be a qubit, and then if we measure, then we have a bit. Somebody could say, yeah, von Neumann entropy is 0. A mathematician would say, actually, inside here there is infinite information, because alpha and beta are infinitely precise number. So we should try to see what we can do about that. So if I think about the requirements that a good definition for physical information should have, then I came up with at least these 4 requirements. So everybody should agree about the information that we have in a state. So it should not depend on the observer. It should be quantized, of course, and countable. It should not be divergent. And finally, if we have a state and nobody touch it, it should not change its information content. So it should be, there should be some conservation law for information. And one of the few things in physics that could hold all these properties is the difference of phase between 2 waves. So what I'm proposing here is to use the difference of phase as the physical entity that encodes information. So every difference of phase will carry physical information. And this is kind of good news in the sense that in quantum mechanics we always do that already. We are already dealing with phases and waves, and so we should be quite good already in dealing with information, which is kind of expected. We are not too far away to already be dealing with information. But we should do it, in my opinion, in a more accountable way, so to try to satisfy the requirements above. So the most interesting one is quantization. So how do we quantize phases? Actually, this turns out to be quite straightforward if you think that probability amplitude in quantum mechanics, and so phases in general, they are simply a vector in the complex plane. We can take the mapping on the Gauss integers, so the integer discrete of this space, and then we can see that we can approximate any phase as much as we like in the limit of a large number of a very large Gauss integer. So by doing that, we can come up with a definition for the quanta of physical information, which I call tesseract, just to distinguish from the bits, which is quite different. So we have the 4 fundamental Gauss integers as quanta of physical information. And as you see here, you can reproduce, in principle, any probability amplitude in the limit of a large number of quanta. And these quanta are different from the bits because they encode a lot of all the properties, actually, of waves and interference and superposition. So what's the emerging view on how the universe, the information universe could be, is summarized in this slide. So on the left, we have a reciprocal space where information quanta are, and on the right, we have the wave function that we are used to. So we can start from this building block from quanta of information to try to build ontological wave functions. So we will place them in the reciprocal space in some modes, and by doing that, we can construct a spectra. This spectra is in the reciprocal space. So already we can answer the answer to the question if where information is located actually is in the reciprocal space, so it does not have any location. This is one aspect of quantum mechanics, like non-locality, which is very well proved by experiment nowadays. So what has a space is the wave function, and this is obtained by a projection from the reciprocal space. And the wave function does not tell where information is, but it tells where this information can be accessed from. So what is bounded by the speed of light is not the exchange of information, which is completely non-local, but the access to this information. And what we can see here is that the observer has a very special role in this, because we can obtain a relativistic invariance, because all the relativistic dependence is in this projection. Sorry, this. Oh, yeah. Now it works. Okay. So by thinking about that, we can also rethink all our how do we interpret quantum mechanics and how all these counterintuitive aspect of quantum mechanics can be seen in terms of physical information. And we immediately realize that we are never measuring particles and we are never measuring waves. We always measure information. And in particular, the information of, for example, a particle being at a certain location or somewhere else. And immediately you come to the conclusion that measurement and interaction are just the same thing. So if we have two states, one could be our detector, one could be our particle, the detector will need to, let's say, exchange some information with this with this state, and this information will not longer be there after the interaction with the detector. So the detector absorbs, or also during the interaction, there will be some exchange of quanta of information among different states. And in principle, we can account from that. This looks very similar to what we do in quantum field theory when we say that all interaction among fields are mediated by the exchange of virtual and real particles. However, there is one interesting requirement that it seems it comes as a necessity directly from this definition of physical information, which is that this information makes sense only if it is conserved in freely propagating states. But if we look back, what this definition says is that these tesseract are carrying quanta of phases. So it means that once they belong to one state, these quanta of phases, they should not dephase. So in other words, the wave function should not spread. So there should be a kind of way that nature, a kind of entanglement potential that nature uses to keep this tesseract phase together. And this is the same principle as that gives us the opportunity to distinguish between states. So if we have a state A and a state B, the only difference among these states, if we look at their spectra, is that this tesseract that you can imagine as small clocks that carry quantized phases, they need to evolve in time all with the same frequency. Otherwise, we will lose the information inside this state. And of course, B can evolve with a different frequency, depending on the details of this spectra. And the only way to distinguish A and B from just their superposition, and in particular an entangled superposition of them, is that in the case this two states will be a unique state, all these tesseracts should evolve keeping their phasor relationship. So how this could look in practice? Here I just want to very briefly show how this could look in practice. And here I propose one equation. So starting from the energy and momentum operator that, as we know in quantum mechanics, and using the Dirac notation, you can write down this expectation value. But at this point is not anymore an expectation value, because here we are dealing with ontological wave function. So this equation would fix the energy of this state to a very specific value. And this makes indeed that in one state all these tesseracts evolve together. In other words, these ontological wave functions are eigenstates of the Hamiltonian. And if we want to briefly look a bit more in detail in that, we can substitute a bomb type wave function where R and S are the real function, and S is usually the action. And we can write down this integral equation. And by looking at this equation, we can even come up with, we can even obtain the special relativity result once we allow us to define the mass as a property of the state itself. So in principle, we can indeed, there's nothing that stops us to define the mass and the properties of particles as intrinsic properties of the information contained in the state. And in this equation, you can also individuate the interaction that has to do with this term, because the only way that two states could interact is by exchange of information, and that exchange is ruled by that term. So once we find out these terms, we can also put them directly inside the action, and we have to define an action that is complex, because it needs to count how many quanta of information are also inside this wave function. So we can redefine the wave function actually in this term, and this means that we just put in the action the fact that we have units that are very well quantized inside the wave function. So in conclusion, this brings to my conclusion. I hope I could give you at least a hint how theory about physical information could look like. And I think key aspect of quantum mechanics have a quite straightforward interpretation if you start to think in terms of quantized phases. And unfortunately, I didn't have time today to go in detail with all of them. But you could already start to look from that perspective. And I believe tesseracts are much more powerful than bits. So I don't think we should always think that nature uses bits, and there's no reason why nature should use bit. And if you're not convinced about that, I would like you to notice another last thing, that is that actually life itself, was not born from the tesseract, from the bits, but from the tesseract. And with this, I would like to conclude, and thank you very much for your attention.
Thank you for this very nice talk. Questions from the audience? By the way, where's the audience microphone, the bouncing cube? I can't see anyone in the audience actually, so if you have a question, just shout and say. Yeah, shout.
Ooh.
You sort of are implying that 2 or 4 states is sort of optimal. Is that true? And isn't 3 better than either?
Sorry, could you?
In other words, you're looking at systems that have a number of states.
Yeah.
Right? And so far, you seem to be using 4 states.
No. You put this for quanta. They are in like we do with from a spectra in the reciprocal space. We can project by Fourier to the real space. There you have all the modes. You just have to fill these modes with these 4 quanta. So you cannot. So it's like the spectra needs to be built from these 4 building blocks, but it can be anything.
Yeah, my point is 4 is just as good as 2, and 3 is better, in a sense, or mathematically I can explain.
I do not completely agree on that, because this is not simply 4, they are orthogonal. I mean, there is interference in this kind of information, and indeed, these are quanta of phases. So bits have nothing to do with phases, in my opinion. So that's, I think, it would be interesting to think in this from this perspective, at least to try to see if it makes sense.